Welcome to Minukuu's Health Tutorials. Today we're going to look at the concept of p-value in concluding a statistical hypothesis test. So now let's try to see how to conclude a statistical test. Assuming we are to conclude this right-tailed statistical test, how do we conclude? Basically, there are different ways of concluding. On the basis of the p-value, you could conclude on the basis of, let me use a pointer. On the basis of p-value and then alpha, we could make our conclusion. Also on the basis of the observed statistic and then the theoretical statistic, we can still conclude. In some cases, we even use intervals with a given confidence level. So there are different ways to conclude. So given this example, how do we conclude? As you can see, in your own opinion, would you say, the difference between, let's assume we are still comparing sample mean to population mean or different population means, and this is the graphical representation of the test results. This is a t-test for that matter. So as you can see, this axis represents the differences in statistical value. At 0, what it means is that there's no difference at all. The difference is 0. In other words, the sample mean would be equal to the population mean at 0. So statisticians after they did their test, they came out with the idea that, okay, if we are comparing means and then we make a sample of size n, and then we assume that the probability of this sample size, assuming the distribution of the sample is similar or equal to the distribution of the population, then what it means is that any results that we obtain on a sample will be the same as that of the population. It will be a true reflection of the population at just a risk of 0.05. So it means 0.05 is the only probability where the sample distribution would not be equal to the population distribution due to sample fluctuation or random sample error. Then what it means is that the only difference would be between 0 and then alpha. Theoretically, if there's nothing that is if there's any extra influence, for example, maybe we have carried out an intervention, we've administered drugs or something, and that has made a change in the parameter, and in this case the mean that we are measuring. If we haven't done anything, or if what we have done is not effective, if we try to make any change and the change is not effective, then what it means is that this difference here, the difference would not be significant. It will just be a reflection of the sample error. So what it means is that between at 0 there is no change in what we call a statistical value, or in other words, distribution between the population and then the sample. So they said, okay, given a particular given sample, this is how it's supposed to be. The only difference would be from 0 to the statistical value alpha, taking into consideration the variance or the standard deviation of the sample, and then the degrees of freedom, in other words, the sample size. This is the difference between, at 0, as I said, it means there's no difference between the sample population value and then the sample value and then the population value. In other words, the population mean, the sample mean. At 0, there's no difference. But due to sample fluctuation, the difference would be between 0 and then T alpha, in other words, the theoretical statistical value. And that difference is due to alpha, which is sample error. Now, in a case where we decided to do our studies on our sample, this is how our sample was supposed to be. But we cannot fix a probability of 0.05 because we have carried out an intervention on our sample. Probably we injected a patient, or we did something like that influenced or that accounted for the increase in mean age, for example. So we cannot fix that probability, and that's why we are doing our test, to know in case the intervention that we carried out never had an effect, then it means the only probability of the change that we observe between our sample values would only be due to the random sample error. But in case something happens, then it means the probability of our sample, what do we call it, the difference that we've observed being due to random sample error would be what, less than the natural or the random sample error, to tell us that okay, the result that we've obtained is not actually due to random sample error, because the probability of it being due to random sample error is lesser than the normal probability, that was like the normal, in other words alpha, theoretically. But in this case, as you can see, we've realized that p is actually greater than the alpha. That's to say there is more probability that the result that we've obtained would be due to random sample error, even if at all there's a difference. In the real population, there will be a higher probability of the results that we've obtained being due to random sample error. So as you can see, that's why I use different inks. This blue portion represents alpha, and then the whole of this green portion, including the blue portion, represents p. So what can we say after all that I've said? What would be our conclusion? Obviously, we could conclude that there is no significant difference on the basis of the p-value, in a sense that the p-value is actually greater than the p-value. When we talk of the p-value, it's all about the surface. That's the surface, that's the probability distribution. We are talking about the surface here. The distribution of the statistical test, t-test, is all about the surface. So as you can see, the p-value, that probability actually covers the whole of this, and then alpha is just this. So it means p-value is actually greater than this. That's why I use, you could see that even here, you see that there's a mixture of the shading to tell you that p actually covers the whole of this, but alpha is only the blue region. So if p is greater than alpha, then it means we have to accept not to accept, you get to know why, but we would definitely fail to reject the null hypothesis. Rejection of null hypothesis doesn't mean we are accepting it, in a sense that probably there might be a difference, that is statistically significant, but we couldn't what should I say, we couldn't prove this difference by our test results, maybe due to lack of test power. Our test power wasn't sufficient enough to prove this difference, probably due to small sample size, or I don't know, maybe other errors or biases. So for that matter, when we fail to reject the null hypothesis, it doesn't mean we've accepted, but we say we cannot affirm or we cannot conclude that there is a statistically significant difference between the actual population results that we are trying to infer or deduce from the sample results. So that's just one way of concluding on the basis of p-value. When p-value is greater than alpha, then we would say there's no significant difference in the population. So as you can see, as I said, at 0, there's no difference between sample population, what do we call it, sample, the sample value and then the population value. But with at what do we call it, at t alpha, this difference is due to alpha, or the random sample error. Now look at our observed difference. The observed difference is the difference between the zero region or the 0 point where there's no difference between the sample error and then wherever our the value that our statistical value has given us, our test statistics or observed statistical value is. So that's between 0 and this. So what can we say based on this? What it means is that when the difference between, or when the observed statistical value is small, then what it means is that we would have a small, if the observed difference that's between our sample values that we let's say m1 minus m2, if that difference is small, then what it means is that, in other words, right now we are inferring the true population. So we would say if mu1 minus mu2, if that difference is actually minute, then what it means is that it will give us a small statistical value or observed statistical value, as we've seen, compared to the difference here. You would see that this small, the observed change or difference is small. Then at that point, as I said, you realize that the observed statistical value becomes smaller than the theoretical statistical value for our sample distribution. So at that point, we can just conclude that there is no significant difference. But maybe if we want to conclude with a p-value, definitely due to this, what will happen? P-value will increase, as you have seen, because if t decreases and then it becomes less than t alpha, t o or t observed t decreases and it becomes less than alpha, what happens? It means the observed statistical value is actually inversely proportional to the p-value. You see that when it decreased, what happens? The p-value increases. And when the p-value increases, it becomes what? Greater than alpha. When it's greater than alpha, what it simply means is that there's a greater chance of the test results being due to what? Random sample error. Remember, p-value is the same as alpha. I would explain why I said so. P-value is the same as alpha in the sense that they are playing the same role. So p-value is actually the observed random sample error probability, and then alpha is a prefix or predefined, or it's a norm. That's to say, if there's no difference at all, if there's no any change either than the random sample error, then the risk of the null hypothesis not being true will be what? Alpha. P-value plays the same role on our observed sample statistic. Also in support of the alternative hypothesis, but against what? The null hypothesis, to say, okay, based on our sample, or what should I say, our observed distribution according to the sample results, for our results to actually, for the null hypothesis to be true, that's to say, if there's no difference, then the probability of this, let's say, of any difference would actually be due to sample error. So we are comparing this model, which is the observed model from our sample, to a theoretical model. So everything, as we showed you earlier on, everything here is the same as this. But so right now, let's say in the case where there's no difference, this has to be the same as this. So we are comparing. It means p-value is the same as this, as alpha. In terms of roles, they are playing the same role. So when we realize that, okay, our observed value, that this real, this theoretical. So if the real thing is the real probability of random sample error is actually greater than the hypothetical probability sample error, then what it means is that there's more probability that the observed results would be due to what? Or the observed change here would be due to random sample error. And we have every right to say that there's no significant differences between the population results, and even if at all there's a difference, it's due to random sample error. That's what it means. So we would say there is no significant difference between let's say the sample mean and the population mean, or the two or more different population means that we are comparing. Let's look at the second scenario. What would you say? As you can see, it's directly opposite to what we've already discussed. Obviously, our p-value is less than alpha, as you can see. This is just the region of p. This is the same concept, so I will not repeat by saying, okay, alpha represents the probability of the null hypothesis not being true due to random sample error. That's to say, alpha is in support of the alternative hypothesis. To say in a real population, if there's no difference between what we are comparing, whether it's mean of population 1 to mean of population 2, if this is really true, then the only probability of this not being true, in other words, the alternative hypothesis being true, would just be due to the random sample error, which is alpha. And that probability of random sample error is alpha. So in other words, we have what our confidence level is 95%. In other words, 1 minus 0.05, and that gives us a probability of what 0.95 if the null hypothesis is going to be true. So in this zone, if the observed statistic falls within this zone, then what it means is that we are not going to reject the null hypothesis, as we've shown here. It observed, but here you can see that the observed statistical value is actually greater than the theoretical value. And because it's greater, as I said earlier on, when t increases, what happens? P-value decreases. So when p-value decreases, what happens? P becomes less than alpha. And when p is less than alpha, what it means is that we are trying to say the probability of the observed difference, if let's say in a real population, the probability of the observed difference being due to random sample error is actually less than the prefixed probability. So that in this difference must be accounted for by something, by a particular change other than random sample error. So at that point, we can say the difference is significant. So if the difference is significant, then we have to reject the null hypothesis, which is saying that the difference is insignificant at a risk of 0.05. So you would conclude that the sample mean, in other words, we would reject the null hypothesis, and by rejecting the null hypothesis, then we accept the alternative hypothesis by saying that the difference is statistically significant. To say the sample mean is not equal to what the population mean, or in the case where we are comparing two or more populations, the mean of population A or 1 is not the same as that of population 2. It's not all about equal to or less than, but as I said, I keep on repeating it. It depends on our initial formulation, depends on the objective of our research, and it depends. We could have said maybe sample mean is less than population mean, and then in that case, the null hypothesis would be what? This is actually our research question. This is what we tried, the difference we tried to prove. Then our alternative hypothesis would have been that since we said this is less than this, then this would either be greater than or equal to this. But that's why I was saying superiority, inferiority, or whatsoever test, it depends on what we are trying to, our objective of the test or the study that we are doing. So as you can see, the observed theoretical difference, considering our sample size, and then the fixing the alpha, in other words, the probability that the difference will be due to random sample error, to be 0.05 if the null hypothesis is true. This is what the difference represents. That's from 0, as I said, there's no difference between the observed sample and then the populations, the observed value, in other words, the observed mean and then the population mean at 0, there's no difference. The population mean, if you create a sample from a population, provided the distribution is the same as that of the population, it means the test results will be the same as that of the population. And what it means is that there won't be any difference. This is a difference in actual statistical value. This is a difference. The horizontal axis represents the difference in statistical value. So here there's no difference, that's 0. But due to random sample error, which is alpha, there's a probability that of 0.05 that there could be this difference, and this difference here is accounted by the random sampling that we did. That probability is 0.05. So that probability is the whole of this region right from here. So in this region we cannot reject the null hypothesis. From here we can reject the null hypothesis if our observed statistic falls within this region. And as you can see, observed statistics is in this region. In other words, is superior to the theoretical statistical value. And when it's superior to this, remember I said observed statistics is inversely proportional to the p-value. When it's superior, it means when it increases, what happens? P-value decreases. And what it means is that when p-value decreases, then it means we have a lesser probability of the observed difference being due to what? Random sample error. We have a lesser probability. Then it means there's something that might have, compared to the prefix or the predefined random sample error. So what it means is that the difference is statistically significant, or that's to say something, if for instance we carried out an intervention, we gave treatment, then probably that difference is due to the treatment and not random sample error. So as you can see, if the observed difference is greater than the theoretical difference, then it means there's something that's responsible for this difference here. So when this observed difference increases, what happens? We have a greater statistical value, and then the greater statistical value, that's to say the observed statistical value would be what? Greater than the theoretical statistical value. Then since observed statistical value is inversely proportional to the p-value, it means there's what? Lesser chance of that's to say if this difference is very large, then what it means is that there's something that's actually responsible for this difference, either than the what do we call it, the random sample error. So what happens? The probability of random sample error would decrease, that is p here, compared to alpha. So hence p will be less than what? Alpha. And then our conclusion is that there is a significant statistical difference between those two or more parameters that we are comparing. In this case, it is because we base all my explanation on mean, then in this case we are trying to say there's a significant difference between the sample mean and the population mean, or the mean of population A or population 1 and then mean of population B, based on the inferences that we've made from our sample studies by calculating what? The observed statistic, which is TO. Thanks for watching, and please subscribe.